Okay, so the first lesson in the 5.10 series is about the derivative of a to the x. And before I get into this, I do want you to recall that we know something that's similar to this. We know that the derivative of e to the x, a very specific constant to the x power, is e to the x. Right? And I know some of you, like I said, this lesson was really easy when we did the e to the x one, and some people really had trouble with it. The idea is really just that when you've got the e to the x function, the derivative will be e to the x. The only thing that makes it complicated is that when there's something up here, we have to use the chain rule. Today's lesson is very similar to this one. The new thing that we're learning today is that if somebody asks you to take the derivative of a to the x, some constant to the x, similar to this, but not the special number e, some, arbitrary constant a, it will be the natural log of a times a to the x, right? So the only difference is that when this, constant base is something that's not e, we multiply by the natural log of that base, right? And what's kind of interesting is even if you were to try and use that for this one, even if you were to say, oh, so shouldn't it be ln e times e to the x? If you were going to try and do this one using this method, remember, what is the natural log of e? The natural log of e is 1, which sort of confirms that the derivative of e to the x really should be just plain e to the x. So for the rest of this video, I just want to race through some examples. I suppose I can leave that there. So for instance, what is the derivative of 3 to the x? Well, it should be ln 3 times 3 to the x. Okay. What about the derivative of 7 to the x? Well, again, 7 is a constant. It's being raised to a variable power. So ln 7 times 7 to the x. In some sense, every single one of these things is going to look exactly the same. They're all just going to look like, what's the derivative of 123 to the x power? Well, it'll be the natural log of 120, well, if I can write my numbers, it'll be easy, of 123, and my L's, times 123 to the x power. Really, really not a big deal. I feel like the only place where these problems really get any bite is when we remember, hey, these are derivatives, which means everything we know about derivatives still applies. If a problem has something plugged into something else, then the chain rule is necessary. If there are functions being multiplied, then the product rule is necessary. If there are functions being divided, then the quotient rule is necessary. And so my next, I think, 3 examples just focus on that. So suppose you knew that f of x was 3 to the 5x minus 1. Right? And I want us to find f prime of x, find the derivative. Right? Well, the derivative of this thing, because it is 3 to, a constant to a variable power, it's going to be the natural log of 3 times 3 to the 5x minus 1. But then, because this power wasn't just x, we need to use the chain rule. So the chain rule has us multiply by 5. Right? So no big deal. I can pretty this up a little bit. Generally, I'm going to take constants and put them in the front. So we'll have like 5 ln 3 times 3 to the 5x minus 1. And that'll be our answer. An important thing to note about this is that this 3, like the 5 can't multiply with this 3 because the 3 has a power on it. And the 5 can't multiply with the 3 here because that's inside a natural log. If you really wanted to, you could take this 5 and put it up here as a power on the 3. It's not necessary, I'm just mentioning it. Okay, so that was my first, more interesting example. This next one I think you should try on your own. Suppose that we had g of x is 6 to the x squared power, and I want us to find g prime of x. If you followed the lesson so far, it shouldn't take you more than 30 seconds to do on your own, so try that one out. So g prime of x, that's a constant base, so it'll be ln 6 times 6 to the x squared, just repeating the original problem, because that's what we're supposed to do. And then because the thing inside of the exponent wasn't just x, the chain rule has us multiplying by 2x. Great, so simplifying a little bit, I'm just going to pull that 2x to the front and say 2x ln 6 times 6 to the x squared. And a lot of times I like to put this stuff in parentheses just because it takes away that temptation of multiplying this 6 and this 6 together. That can be a strong temptation, so take care with that. And that's this answer. The last answer I have is, or the last example I have is the most complicated, and I still don't think it's that bad. Let's take a look. So, find the derivative. Find the derivative of x cubed times 4 to the x squared minus 1. I think the biggest thing to recognize here is just that this is going to be a product rule. So make sure you do the product rule. The two things being multiplied are x cubed and 4 to the x squared minus 1, so they'll just take turns being the derivative. So first, the derivative of x cubed is 3x squared, and we leave the other thing alone, because that's how the product rule works. Plus, this time I'll leave the x cubed alone, and I'll multiply by the derivative of this thing, which is going to be some work. Right? The derivative of that is, well, it's a constant to a variable power, so it starts with ln 4 times the original function, 4 to the x squared minus 1, times the chain rule, which gives us 2x. Right? Then in some sense, yay, I mean, that's the derivative, right? The top line was the original function. This gives me the derivative, right? And so how can we simplify that? You know, a lot of times when we've got product rules like this, I like us to think about factoring. So what do they have in common? Well, they both have this 4 to the x squared minus 1, and they both have a term of x squared. I mean, we could pull an x squared as part of that. So if I were to pull that stuff together, if I take out x squared times 4 to the x squared minus 1, the first term only has 3 left, and the other terms have x from this and 2x from this, so that makes 2x squared times that natural log of 4. And that, I think, is probably the best we can do for the derivative of this one. Formally, that's more or less the end of this video. I am going to go ahead and take one more minute to show where this formula comes from. So if you're interested in seeing that, if you like knowing where things come from, hang out with me for one more minute. So showing where this comes from, it helps for us to understand a really sneaky way to rewrite a number like 2. Right? 2 is effectively the same thing as e to the natural log of 2. Right? So if you think about it, how could we rewrite 2 to the x power? We could rewrite 2 to the x as e to the ln 2 to the x. Which means, and actually let me go one step further, I could actually make that e to the ln 2 times x, because that's how exponents work. If you have a power raised to a power, you can just multiply the powers. So where this gets a little bit fun is if somebody says, hey, what's the derivative of 2 to the x? If you wanted to, you could think of that as the derivative of e to the ln 2x. Now, I know nobody in their right mind would do that. Like, once you know the formulas from today, just do this. It's not that hard. But this is explaining where that formula comes from. So how would I do this derivative? Well, e to anything is e to that thing. But because my power isn't just x, I have to multiply by its derivative. The derivative of natural log 2 times x is ln 2, right? But then remember, wasn't this e to the ln 2x? Wasn't this just a fancy way of writing 2 to the x? So this boils down to being 2 to the x times ln 2, which is exactly what our formula would expect us to get from the derivative of 2 to the x. So hope you enjoy seeing where that comes from, if you even watched this far. So I will see you in the next video.